All right, guys, welcome to the next video, and this time we're going to look at Hess's law and energy cycles. This can get really tricky, but you're going to need a calculator. So I'd pause the video now and get yourself a calculator, just so you can double check whilst I'm going through this. And you're going to have to do your own, so we might as well make sure you've got one ready. Right, with Hess law and energy cycles, a bit like how we did with rates, I want to turn this into a puzzle, and I'm going to teach you guys the rules. So there are a few rules of Hess law and energy cycles that we need to know. But when you see anything in the fashion that looks like the question here below, ignore the triangle bit, you're going to see something that looks like this, a table with substances and numbers. And after you've seen a few of them, you'll know what type of question they're going to ask you. I need to teach you the rules of how to do this, and then we can work together and get the final answer. Let me tell you some facts of how this works, first of all, and then I will try and explain my best. You don't need to understand it, but you do need to be able to recall this definition. So, Hess's law. This is the total enthalpy change of a reaction is always the same no matter which route is taken. So it's the energy change of a reaction is always the same no matter which route you take. So let's take this example here and let me explain. So in order to do this reaction, where we had the decomposition of nitrogen dioxide into this, that's the one way we can measure the reaction. But let's say, for example, we can't do this reaction. It just doesn't work. Maybe we need ungodly amounts of energy or something else is in the way. However, what we can do is we can decompose it into this. And if I react these two things together, I can get these products as well. So I found a different route. Now, what's interesting with Hess law is, like I said before, that regardless of the route that you take, the enthalpy change is always the same. So the enthalpy change from going from route 2A and then to 2B is two reactions, but if you add up the energy of those two things, you get the same as route 1. And that's the most interesting part about it. Now you're going to be asked to determine the energies of those routes using those rules. This is where it gets a bit tough, and I'm going to teach you a couple of tricks that should make your life a little bit easier to approach these questions. Right, let's start off with this example here so you can see what an example might look like. We're going to do the following method for the calculations when we're given the enthalpy change of combustion. So this is where we have to learn our first rule. For Hess law, there are two of the most common things you'll bump into: enthalpy of combustion data and enthalpy of formation data. Anything in between, you might have to do this triangle type thing and work out products over reactants, or product takeaway reactants, and that should work as well. But I'm going to teach you the trick. So we're looking at enthalpy of combustion data. What we've got is a reaction where we are going to determine over here the formation of butane. So not the combustion of butane, but the formation of it. And we don't have formation data, so we can't add up the numbers to work it out. We have to do a different route. So the question wants us to do is to find the enthalpy of formation for this. Remember, it's enthalpy of formation, it's butane from its elements. But we've only been given the combustion data, which means when I burn carbon and make CO2, I release this much. When I burn hydrogen and I make water, I make this much. And then when I burn butane, I make this much. So that's the information we've been given. That's the other route. And you can see below, I've put it into a triangle. Now, you are going to have to form these triangles, and I'll teach you. I'm just talking you through what you can see. So we've got some data over here. When we identify this is what we start with. This is what we finish with. And we want to know what is the value of that purple arrow. And we need to go this way. We have to go that long route. Right. Now, you can read the instructions on the screen. This is more for your booklet, but I'm going to take you through them anyway. So I'm going to teach you a method that I call the tramline method. So it's a bit like tram lines, and I'll explain how this works with this. So we want to go from point A to point B. Let's say that's from Manchester to Bury. So let's go from Manchester to Bury. And let's say, for example, you live at Heaton Park. So if you want to go from Heaton Park to Bury, you're probably going to go from here to here. But if you wanted to go from Heaton Park to Manchester, you're going to have to go from here to here. And I'm going to use some terrible numbers here, but I'm just going to say that you going from Heaton Park to Bury is going to be 400 meters. I know that's not true. And then you going from Heaton Park to Manchester is going to be 100 meters. When I ask you the question, how far is it from Manchester to Bury? You can see immediately it's 500. Really straightforward, it's 500. You've done that because you've added those two arrows together. What you didn't take into account is that the 400 meters is you going from Heaton Park to Bury is positive because you're going in the right direction. But you going from Heaton Park to Manchester is negative because you're going the opposite direction that you want to go. This will still give you the answer 500 meters, but there is another thing that you must do. You need to reverse the sign of the arrow that is going the wrong direction. So the negative 100 meters, if we were to add those together, we get 300 meters, and we know that Bury and Manchester isn't going to be that 300 meters. It is 500. The reason why is because this red arrow is pointing the wrong direction. So we're going to flip this arrow to make sure it's pointing in the right direction. The only thing that changes is the sign. It's still 100-meter long, but now it's positive. So that's where that's changed. This relates to Hess law because we're going to do the same exact method for that. And what I mean by that is we are going to draw the purple arrow first. This is the one that we want to determine. So I'm going to draw an arrow here just like that. Next, we need to determine the value of the other arrows. You can see I've already done these values for you, but let me talk you through them. So the enthalpy of combustion for butane is going to go to this direction. And over here, we've got the products of combustion. So if I burn C4H10, I release this much energy and I make these products. These products here don't matter. That's okay. Going down, I can even say combustion products. Again, this bottom part of the triangle doesn't matter. So I've got negative 2876.5. So that is going to be my red arrow. Is my red arrow pointing toward my products or away from my products? Pointing away, which means we're going the wrong direction. So our red arrow is going to be here like that. The blue arrow. This is where it gets a bit more complicated. Let me explain. This time we're looking at combustion data. When we combust carbon, we release 393.5 per mole. How many moles of carbon do I have? 4. So I multiply this by 4. Hydrogen. If I burn 1, I get negative 285.8. But I've got 5, so I'm going to burn 5 of them. I'm then going to add these two things together. And this arrow is pointing in the right direction of my products because you can see, if I want to go from here to here, I have to go this way round. And you can see that this blue arrow follows that path, and that's okay. So I'm going to draw this one going this way, like this. And you will draw these arrows too, maybe a bit straighter than mine. Let's move that one. There we go. So that blue arrow is going to be this value right here. So I'll add those two things together for you. I'm just going to do the math right now. And I'm going to get a value of negative 3003. It's really important you keep these negatives where they are. So input that into a calculator exactly as it is. I'm going to put a plus sign here to remind myself that I'm just going to add these two arrows together. And don't worry, I will remember to flip them. The red arrow has a value of negative 2876.5. But like we said earlier, that red arrow is pointing the wrong way. So we're going to flip this arrow. And you know what? I will literally flip this arrow. So let's rotate that around. Let's extend that out. I've changed the angle of it. It's going to really annoy me. But there we are. I flipped the arrow, so now I'm going to make this sign positive. Notice this is still negative. That's fine. We don't change that blue arrow. That blue arrow stays the exact same. But now what we do is we add the blue arrow to the red arrow, and we're going to get our final answer. So in your calculator, this is the way that I would put it in. And yes, it does sound weird. I would put in negative 3003 plus two pluses, 2876.5, enter, or equals. And you should get a value, and I would love for you to check this, is negative 126.5 kilojoules per mole. Please double check this on your calculator and make sure that you're getting the same answer as me. If you're not, then something's definitely going to go wrong. Now, for combustion data, if you have delta C on there, you're going to have to draw one of these triangles yourself. And this is where it gets a little bit tough because some of you might struggle with that. Now for combustion, if you've got delta HC in the table, your arrows are pointing down. This one's going down, this one's going down. And the way that I remember it is combustion is burning it down to the ground. So we're going to burn it down to the ground. That's going to give us our arrow direction, and that's going to help us build that tram line. So we should be able to work it out from there. These are the rules of the game of Hess law, and there are quite a few steps that you need to take into account, but you could get anywhere between 4 and 6 marks for this, so it's definitely worth practicing. Let me move on to the next one over here. And this time, you can see we've got something slightly differently. What we're going to do is we're going to look at something else. We're now looking at formation. This one was combustion data. This is now formation data. And for formation data, we're going to notice that in our data, we have this F here. If we've got F, we're forming it. And I see it as we're forming it from the ground up. So we're forming it from the ground up. That means our arrows will be pointing up in our triangle. In the top part, we're going to have our reactants. What do we start with? At the end, we're going to have our reactants. Our product, sorry, what do we finish with? And then down here, we're going to have our new route of direction, which we're going to build ourselves. So again, you're going to form some tram lines just like you did before. And this time you can see the maths is already on the screen. So I've already worked these things out for you, but let's go through it really, really quickly because I'm thinking you're going to get bored of me soon. So I've got our hexane and I'm going to completely combust it to produce CO2 and H2O. Do I have combustion data to work that arrow out? No, I don't. So I need to do something else. Let's draw our arrows in. We've got let's stick with the same colors. Got our blue arrow over here and got our red arrow over here. And the purple arrow I'll keep here at the top. You can see I've already done some of the maths on screen, so there's no stress there. What we need to do is determine the value of that purple arrow. And this is how we do it. So the first thing that we've got is we've got our reactants here. Now, let me explain some of these numbers. Because we've been given formation data, it's how much energy is released when this is formed from elements under standard states and conditions. These are our elements down here. You don't even need to write this bit. You don't even need this bit. You could just literally get away with saying elements. And I think it's even easier. If we're using formation data, we write elements at the bottom, we form them up. So for C6H12, in order for me to form 1 mole of it, I need negative 156.3. So that's where that number's come from. For oxygen, you can see I need 9 of them, but I got 0. It doesn't take any energy to form O2 gas from O2 gas because O2 gas going to O2 gas. What has changed? Nothing. There is no change, so therefore there is no enthalpy change. So an element from its own formation is 0. So if it's just an element, it's just going to be 0. There's our 0. On the other side, we've got some more mass that we need to do. When I form CO2 from its elements, I release negative 393.5. And I've got 6 of them, so I multiply that by 6. For water, I produce 6 as well. And then you can see there, I've multiplied that by 6. And then we're going to add those two things together. I'm not going to do the maths for you this time. I want you guys to do this one. So what I'm going to do is I'm going to draw the arrows to hopefully help you out. I'm going to have a purple arrow there. Going to have a blue arrow over here. And we're going to have our red arrow over here. The reason why I've drawn it this way, remember, we're going from left to right, so this direction. Is the blue arrow going in that direction? No, it's not, so it's going backwards. And the red arrow is going in this direction, so we keep that going forwards. And this time it's the blue arrows we're going to have to flip. Have a go at doing that and get yourself a final answer. Right. What I've got for you as an additional task is to have a go at these questions down here. So you can see this one is going to use our enthalpy of combustion data to find the formation, that top arrow. And the bottom one is now using our formation data, but we want to find our enthalpy of combustion. So going from left to right. What I'd like to do is having a look at these, can you determine the values and prove that these values down here are correct? One note, this question over here gives you the enthalpy change of combustion of ethanol, but it's not told you what the actual balanced equation is. Start by balancing the equation. Remember, CHO and it's an alcohol, so we have to use -1. If you're unsure, you're gonna have to go back and watch another video, but I think I'm gonna leave this one here with you. Have a go at this, and we'll have some more practice in class.